Okay, so today we're going to talk about complete and net ionic equations, equations with ions. The reason why we have to do that is because what we said isn't really true. And I tried to prove that to you yesterday. Because we write H2SO4 AQ, right? Sulfuric acid. But when I put the sulfuric acid solution on with a conductivity light bulb, the light bulb came on. And that tells me that there's no H2SO4, because H2SO4 is neutral. It doesn't have a charge. Okay? But in order to conduct electricity, you have to have charges moving. So there really is no H2SO4. It's really H plus and SO4 2 minus. That ionic compounds fall apart into ions when you dissolve them. That's why they conduct electricity, okay, when they're dissolved. Okay? So there is no H2SO4 aqueous. So we have to understand what we're really writing, because we shouldn't write a lie without knowing what the lie really is. Okay? So that's the idea behind what we're doing. Because every aqueous, in a complete ionic equation, every aqueous compound is written as separate ions. So we just take and separate the ions out. So, and solids, liquids, and gases are written as whole compounds because they haven't fallen apart into ions. A solid, the ions come together. It doesn't have a charge anymore. Compounds don't have a charge. Gases don't have a charge. Because if they had a charge, they'd be able to hang on and they wouldn't be gases anymore. And liquids, that's the reason why making water causes a double replacement reaction to happen. Because you're taking separate ions and putting them together. That's the liquid we usually make. So we write stuff like this. Magnesium chloride and lead 2 sulfate make magnesium sulfate and lead 2 chloride. We've been doing this for a week now, right? But notice 3 of those are aqueous and 1's a solid. So what you really have is, you don't have MgCl2 and PbSO4. You have Mg2 plus and Cl minus. You don't have PbSO4, you have Pb2 plus and SO4 2 minus. You don't have MgSO4. You have Mg2 plus and SO4 2 minus. And you don't have PbCl. You do have PbCl2 because it's a solid. Solids don't fall apart. Aqueous do. So all I did was take this and make it into its 2 ions. Magnesium and chloride. Lead and sulfate. Mercury and sulfate, but the lead 2 chloride was solid, so it stayed together. I should be, I didn't type it. Actually, I think what happens if I try to type it, it goes off the screen, but there should be a 2 minus there. They all should be ions. Everybody okay with that? That's what's really in the dish. Okay? This is really what happened. If I say MgCl2, it's all if it's dissolved, it's falling apart. There's no MgCl2. There's Mg2 pluses and there's Cl minuses. Okay? So that's the complete ionic equation. All you do is take your equation and take everything that's an ion and write it that way. So if you had iron 3 bromide and potassium hydroxide making potassium bromide and iron 3 hydroxide. Oh, where did that go? Okay. So all you have to do with an equation like this is just look at it and say, is there any FeBr3? Well, is FeBr3 solid, liquid, or gas? No, it's aqueous. If it's aqueous, it's really Fe3 plus and Br minus. Because our name is iron 3 bromide, so we got iron 3 and we got bromide. So all we do is just pull the ions apart. It's a lot of writing, I know, but we'll shorten it later. We're going to start off here, we'll shorten it later. And KOH, there's really no K, or OH, there's really K plus and OH minus. There's no KOH, it's K plus and OH minus. There's hydroxide ions and potassium ions. Because everything falls apart when I dissolve it in water. That's what ionic compounds do. The ions fall apart. Okay, I'm going to make KBr. Is there really any KBr? Well, it says aqueous next to KBr, right? So I split the KBr. And iron 3 hydroxide. Is there really iron 3 hydroxide? It says solid, so yes, there really is iron 3 hydroxide. So I leave that together. Ta-da. Really difficult? No, tedious again, right? Tedious. But we're trying to make a point here, and the point is why that light went out. Yeah. For right now, yeah, because that's what we're trying to emphasize is that that's what's going on. Okay. You don't have to write a bunch of these, by the way. I'm reasonable. I just got to make sure you got the main idea. Okay, so you just wrote that, right? But look at this. I started off with Br minus, ended up with Br minus. And I started off with K plus, and I ended up with K plus. K plus and Br minus don't change. They were just there for the ride. So K plus and Br minus in this situation are given a name. Since they didn't do anything and just sat back and watched, they are called spectator ions because they didn't change. So the ions that don't change are spectators. Since they don't really change, do I need to put them there? I started off with them and I ended up with them. They don't change in anything, right? So I could just get rid of those. If I got rid of the K and the Br on beginning and end, eliminate the spectators, things you're not allowed to do at sporting events. Oh no, there was an Italian team that wasn't allowed to have, at its home games, was not allowed to have a crowd because their crowd was too awful. The crowd was so bad that they had to play all their home games to an empty stadium. But that's what happens. You have to eliminate the spectators, not the goal of the thing, but eliminate them. So if I eliminate it, what am I left with? Well, I'm left with Fe3 plus and OH minus makes FeOH3. And these are the things that really changed. Right? I know, does it bother you it's not balanced? It should be easy to balance though, right? I'd have to put a 3 in front of OH, there we go. Notice I didn't try to balance the complete ionic equation. No reason to balance the complete one. Just say what's all there. Okay? Balance this one. And by the way, when you write this one, it's not complete anymore. So I can't call it the complete ionic equation anymore. So I call it the net ionic equation. Okay? Net. Okay. Place where you see this word net used this way. A paycheck. Okay. If you make $10 an hour and you work 10 hours, at the end of that, for that 10 hours, you've earned $100. But they give you a check, it's not for $100. It's for less than $100 because they take out some taxes. This guy named FICA takes part of your money. Who's FICA and why do they get my money? Well, FICA is Social Security. Okay. But at the bottom, your check for $87, what they say above that is net pay, what you really get. Net is what it adds up to at the end. This is what what we really get is, let's just eliminate the spectators. And it needs to be balanced in terms of both mass and charge. So just mass is not alone, because if you don't have the charge balance, you created and destroyed electrons, you don't have that kind of power. You wouldn't be here. Okay. And that would explain why the light bulb went out yesterday. So let's try a couple of these. Write the net ionic equation for this. Aluminum and iron 2 sulfate makes aluminum sulfate and iron. Al plus FeSO4 makes Al2SO4 3 plus Fe. Okay, well, is aluminum really there? Is it aqueous? Does aluminum dissolve in water? No. So I'm really going to have aluminum. Is there iron 2 sulfate? Is there really iron 2 sulfate? It says aqueous. So it's really Fe2 plus and SO4 2 minus. Is there really aluminum sulfate? No, it's aqueous. It falls apart into ions. And the ions are Al plus and SO4 2 minus. Is there really iron? Iron's a solid, right? It's not going to dissolve in water, so. Okay, so there's the complete ionic equation for this. Any spectators? Does aluminum change? Yeah, aluminum loses electrons. Does iron change? Yeah, iron gains electrons. Does sulfate change? No, so sulfate is the spectator. So I'm left with aluminum plus Fe2 plus makes aluminum 3 plus plus Fe. And that looks balanced because there's one of everything, except it's not balanced. Because the left-hand side has a charge of 2 plus, and the right-hand side has a charge of 3 plus. Where are 2 plus and 3 plus going to run into each other? At 6, right? So I'm going to have 3 Fe and 2 Als to get my ions right, which is going to be easy to balance because now I need 2 Als here and 3 Fes there. These are not random numbers. The original equation wasn't balanced. And if you went to balance that original equation, you say, oh, there's 3 sulfates. I got to put a 3 in front of FeSO4, which means I'm going to have to put a 3 in front of Fe. There's 2 aluminum, so I have to put a 2 there. Notice those coefficients still work out. This still says 3 Fe2 pluses and 2 Al3 pluses. See how they're still there? Okay, so this is the final result. Eliminate the spectators, balance it according to charge. On double replacement, the charge will balance easily. On single replacement, you're going to have to watch out to make sure that the ions have if the ions don't have the same charge, you're going to have to fix that. Make sense? Mm-hmm. Okay, so, oh, that's not what I clicked on, guys. That is not what I clicked on. We did that one a long time ago. It was this one. What the heck? Why is that doing that? I clicked on the same one. What's it doing? I want slide. There it is. This time it worked. Okay. All right. See if we can save ourselves some time. Okay. Look at all the aqueous and the solid pieces on here. What am I really going to make? I'm really going to make MgCO3. That's what I'm really going to see, right? So I know that I'm really going to make MgCO3. Now it won't let me write. Okay, I'm really going to make MgCO3. What ions would go into making MgCO3? Mg 2 plus and CO3 2 minus. Now think about if I tore all these apart. I'd take the K plus and then have the CO3 2 minus. I'd have the Mg 2 plus and the I minus. On the other side, I'd have the MgCO3 and I'd have the K plus and the I minus. The K plus and the I minus are my spectators. So if you know what the solid is, that's what's going to be changed. You've got to make sure nothing over here was solid to start with. Because if it started off as a solid, you got to leave it together. Does that make sense? Okay. Change this later. This really should be Cl2 gas because we can't get chlorine down to negative 100 degrees Celsius before it turned into a solid. It should be a gas. Okay, so let's look and see what really happened here. When I start off, is there really Cl2? Yeah, so I'm going to have to write that. Is there really NaI? No, it's aqueous. But I don't know which piece I need yet. But I know it's not, I don't need all of it. Okay, is there really NaCl? Well, NaCl says aqueous, so no, there's no NaCl. Is there really I2? I2 is a solid. So I got to do that. So now I got the Na, I, and Cl ions. On the reactant side, I need the I minus ion. And on the product side, I need the Cl minus ion. Everybody okay with that? Because I know the Cl and the Cl2 and the I2 got to be there. So the ion I need to make I2 is the I minus. The ion I need to use the ion I get when I break up Cl2 is the Cl minus. Is it balanced? Nah, put 2 there. Get my 2 I's, put 2 there to get my 2 Cl's. My left-hand side is 2 negative. My right-hand side is 2 negative. This is balanced. Yeah.
Why on the left side is an iodine?
Because it's not by itself, and it's not neutral. It's stolen an electron from sodium to get to noble gas configuration. It doesn't need to hook to another I. It's already got noble gas configuration by stealing that electron. Okay, so we're still back to noble gas configuration. Make sense? Okay, and you can only write net ionic equations. We only write them for single and double replacement. I could talk to you 1,000 times, but you just get tired of copying my examples. I've shown you what can change, so here you go. And there are not 100 of them.